This is workshop 6, and we're going to start you off with two very similar questions. I will remind you, however, what's involved in doing these, but I think that you might want to look at both of the questions at the same time, and then we'll take votes on them separately. They can be very simple yes-no votes. Now, there's going to be a relation. This is the Greek letter rho, in case you haven't seen it before. So that's a rho, which is another perfectly good letter you could use for relations. And I'm going to define a relation on Z by x is related to y if and only if x squared plus y squared is divisible by 3, if 3 goes into x squared plus y squared. And you're asked, is rho an equivalence relation on Z? I'll remind you that's the question is it reflexive, symmetric, and transitive? So is rho reflexive, symmetric, and transitive? So it needs to be all three. Now, if you show that any of them fail, then you could stop because it's not an equivalence relation, but I recommend that you have a go anyway at all three just to try and convince yourself. The most interesting one here, I think, is transitive. That's the least obvious of them. So, so I think you should be able to figure out reflexive and symmetric. Now, what does reflexive mean? So rho is reflexive if for all integers or all x and z we have x is related to x, not just some but all. Rho is symmetric if for all x and y and z it's true we have that x is related to y implies y is related to x. And rho is transitive if for all x, y, and z in Z, if x is related to y and y is related to z, then x must be related to z as well. Okay? So those are the three things you're investigating. Now, as soon as one of them fails, it's not an equivalence relation. But if all three of them are true, it is an equivalence relation. And once you've done it in question 1, where you look at 3 dividing into x squared plus y squared, you can have a look at question 2, where you're looking at 2 dividing into x squared plus y squared. So I suggest you try both. And we'll come around and see how you're doing, and then I'll decide whether to take the votes separately or whether we'll just do the votes one after the other. We'll see if you can get both of these sorted. Okay, so we'll come around and help you with these. Right, I'll pause the recording there, and we'll come around. On question 1. Got 24 answers so far, so a lot of people haven't voted yet on question 1. Okay, we'll get, let's see what you've got. 36 answers, 42 answers, okay. Most people agree that it is not an equivalence relation. Okay, that's correct. Before I forget, I'm going to zero the votes on that. Well, no, I'll zero the votes on that in a minute, but I'll try not to forget. Okay, so the correct answer is it's not an equivalence relation. It's not reflexive. For a start, for example, 1 is not related to 1. That's supposed to be not related to. I'll just do that again. 1 is not related to 1 because 3 does not divide 1 squared plus 1 squared, which is 2. Okay? You should give a specific example. You see, 3 is related to 3, 0 is related to 0. There are some numbers which are related to themselves, but there are also some numbers which are not related to themselves, and that's what matters here. Okay? So it's not reflexive. It is symmetric and it is transitive, which is a bit odd. The reflexive is easy. The symmetric is easy because x squared plus y squared equals y squared plus x squared. So I would say it's clearly symmetric. But the transitive is far less obvious, and it turns out, I think I won't give you the details of this now, this is an exercise that it's actually quite difficult for x to be related to y. It turns out to happen if and only if x and y are both divisible by 3. So here's an exercise. X is related to y if and only if x and y are both divisible by 3. Now that's not obvious, and so I leave it as an exercise, but you'll get a better idea of how to do that exercise once we've looked at some other questions. Okay? It's best to work modulo 3, and modulo 3, if you square any integer, you always either get 0 or 1, which makes it very hard to add two of them to get 0. 1 plus 0 and 1 plus 1 don't work, so the only way to add a 0 and a 1 to get 0 mod 3 is to add 0 to 0. That's the reason. Okay, but more details on that coming up later, on that sort of thing. So once you realise that it's actually quite hard for x to be related to y, and it's the same as both being divisible by 3, it's much more obvious that it's symmetric and not reflexive and is transitive. Because if x is related to y, then they're both divisible by 3. And if y is related to z, then they're both divisible by 3. And then, once you've got both of those, x and z were both divisible by 3 as well, and you're done. Okay. So some of that is left as an exercise. Right, now, I think some of you need a bit more time on question 2. I'm going to come around and see how far people have got on question 2. I'll stop the recording again, pause the recording again. Think again. Okay, let's see what you've gone for. Okay, we've got third line answers so far with the majority in favour of B, which is correct. Okay, this is an equivalence relation. Let me just quickly show you, I'll tell you two reasons for this. One is I'll give you the slow systematic one and then I'll point out the shortcut afterwards. Okay, so let's do the slow systematic one. So we'll check the conditions, we'll check reflexive. Let x be in Z. Is x related to x? Oh, it's R2 this time. Okay, is x R2x? Well, you have to look at x squared plus x squared. That's yes, because x squared plus x squared plus x squared equals 2x squared is divisible by 2. So when you plug y equals x in here, you do get that 2 goes into 2x squared. So that's fine. Symmetry is as before. It's obviously symmetric because x squared plus y squared equals y squared plus x squared. Symmetry, when it's true, is usually quick. And again, without using the shortcut, I'm going to prove it's transitive. Now, if you haven't spotted the shortcut, this is the bit that's least obvious. Okay? Suppose x is related R2. I wish I'd used rho. Suppose x R2y and y R2z. Then 2 divides x squared plus y squared, and 2 divides y squared plus z squared. Now if you add two even numbers, you get an even number, so I can add those two. So 2 divides x squared plus y squared plus y squared plus z squared, which is equal to x squared plus z squared plus 2y squared. So this is even, but 2y squared is even as well. So x squared plus z squared must be even as well. Or you can do it all modulo 2. But the main thing is here, we've now proven that if you assume that x is related to y and y is related to z, you end up with x related to z, and you've proven transitivity. And what's the shortcut for the whole thing? Oh, anybody spot the shortcut for the whole thing? The shortcut for the whole thing is that R2 is actually the same as congruence modulo 2. So R2 is congruence modulo 2 in disguise. The reason for that is for all x and y in Z, we have x squared is actually the same as x mod 2. You can check. Y squared is, of course, the same as y mod 2. But that's also the same as minus y mod 2. Mod 2 is very nice. So x squared plus y squared is actually congruent to x minus y mod 2. And so you get 2 divides x squared plus y squared if and only if x squared plus y squared, that's supposed to be if and only if and only if x squared plus y squared is congruent to 0 mod 2. That's another way of saying divisible by 2, which is if and only if x minus y is congruent to 0 mod 2, which is another way of saying that x is congruent to y mod 2. And congruence mod 2 is a standard equivalence relation which you're allowed to quote, unless you're being asked to prove that congruence mod 2 is an equivalence relation. So, so that's a shortcut if you spot it. except, of course, I had to prove that it was, I had to demonstrate to you that it was the same as congruence mod 2, but at least if you spot it's congruence mod 2, then you already know the answer. Right, any questions about those two relations? If not, we'll move you on to question 3, and I shall zero, let's see, I shall zero the votes before I forget. And I'll just remind you about a couple of useful facts of Module 11. Obviously, 1 is congruent to 1 mod 11. 10 is congruent to minus 1 mod 11. 100 is congruent to plus 1 mod 11. And it alternates. 10 to the n is congruent to minus 1 to the n mod 11. So the quickest way to do this question may be to do some work with the digits. On the other hand, you might spot what these numbers actually are, and that will give you another way of doing it. So 2 different ways that I recommend to do this, or third way, you could do long division divided by 11, but I think that's the slowest. Okay, so I'll let you think about those. We'll come round and see if anybody's made any progress on that, and then we'll get some votes. I'll just start the recording again. We've got massive agreement here. Look at that. 76 to 0. Okay. Oh, somebody decided to. Okay, so yes, the ones that are divisible by 11 are these ones. So I said what you have to do is, you see how much are they worth mod 11, and you add them all up mod 11 to figure out how much it's worth, and if you get naught, or something that's divisible by 11, then you're divisible by 11. So this one, you have to do 1 minus 2 plus 3 minus 2 plus 1. So 1 minus 2 plus 3 minus 2 plus 1, I think is 1. So this is congruent to 1 mod 11, which means it's not divisible by 11. Whereas this one, 1 take away 2 plus 3 take away 4 plus 3 take away 2 plus 1, that does come out as naught. So this one is divisible by 11. Let's just check I got it right, so let's have a look. 1 plus 3, 4, 7, 8. And then you're losing 2, 6, 8. So that's naught. So 1, 2, 3, 4, 3, 2, 1 is congruent to naught mod 11. Congruent to naught means divisible by, so that one's divisible by 11, and so on. So you can go through those and see what they are, or note that 1, 2, 3, 2, 1 is equal to 111 squared. 1, 2, 3, 4, 3, 2, 1 is equal to 1, 1, 1, 1 squared, etc. And you can use that to work with and give you a slight shortcut. If you remember facts about prime numbers, remember 11's prime. So 11 will divide the square of a number if and only if 11 divides the number itself, and these numbers are rather more obvious. You can see which ones are divisible by 11 straight away. So that's 2 different approaches to that. Any questions about this modulo 11 stuff? If not, we'll move on to modulo 7. Oh, yes, sorry?
Just out of interest, if you hadn't seen it before, was there any easy way to spot that they were the ones
No, I don't think so. It's just that some people happen to know that those are the squares of those numbers. Some people have fun messing around with numbers, and used to have. I had a book when I was small called Adventures with Your Pocket Calculator or something, and it said, look at these fun patterns you can get when you mess around with these numbers. So you might have just happened to know. Right, okay, so now we move on to this interesting bit. So, what does it mean to be a square modulo k? It means that the sum integer, which when you square it, leaves remainder r mod k. Well, okay, it's congruent to r mod k. We're going to be looking at modulo 7. Our modulo 7, the possible remainders really are 0, 1, 2, up to 6. Though sometimes you can think of -3, -2, and so on up to 3, because you get one of each kind there as well. These aren't officially the remainders, but it is true that each of these numbers is congruent to one of these, mod 7. Like 6 is congruent to -1, 5 is congruent to -2, and 4 is congruent to -3. If you want to square things, it's sometimes quicker to use these ones, because the -1 squared is the same as the plus ones. So what you're supposed to do in this question is square these things and see what you get modulo 7, and everything else squared will be one of those modulo 7, because everything is congruent to one of these mod 7. So the first thing you can do is work out which of 0, 1, 2 up to 6 are congruent to the square of some integer. And you should just square these numbers and see what you get modulo 7. And there aren't very many of them. Okay? So how many of these integers, 0, 1, 2 up to 6, are squares modulo 7? And all you need to do is square these things and see what you get modulo 7, which of these ones are congruent to squares modulo 7. Any other integer, you just get repeats, so you only have to check a few. Okay, we'll let you have a go at that. And probably what you should do is, if you figure that one out, go on and try question 5, because what we'll do is, just at the end, I'll run through both question 4 and question 5 for you. Let me zero the votes while I'm at it. Okay, the votes are zeroed. I'm now going to pause the recording. So, anyone who hasn't voted and who thinks that they've got an idea should vote now. And let's see what you've gone for. 28 responses with some disagreements, but with, well, big minority going to C, but still the most popular answer is D, which is that 4 of them are, which is the correct answer. Okay. So 0 squared is 0. Okay, that's congruent to 0, mod 7. 1 squared is congruent to 1 mod 7. 2 squared is congruent to 4 mod 7. Well, it's equal 4. 3 squared is 9, which is congruent to 2 mod 7. And those are the 4 you can get. And you can't get anything else, but why not? Well, 4 squared is congruent to -3. 4 is the same as -3. That's the same as 3 squared, so that's just a repeat of the 3 squared. Okay, so I haven't got anything new. 5 squared is congruent to -2 squared, is congruent to 2 squared, so that's nothing new. 6 squared is congruent to -1 squared, congruent to 1, mod 7. This is all mod 7. Nothing new there. 7 is the same as 0, so 7 squared is the same as 0 squared. 8 squared is the same as 1 squared. 9 squared is the same as 2 squared. Nothing new there. -1 is the same as 6. -2 is the same as 5. Nothing new there. Any other integer, you just get repeats. So the rest are all repeats. So these are the only ones you can get. 0, 1, 2, or 4. So 0, 1, and 2, and 4 are the only squares modulo 7 in that range between 0 and 6. Any other square, any square is congruent to one of those 4 numbers. And that's how you do question 5. Oh, but first, just any questions about that one? Okay, so you only have to check, you really only have to check 7 squares, but then it turns out that because minus number squared is the same as plus number squares, you really only have to check 4 squares and then you're finished. And some of those might have repeated, but they didn't. Now, if you do modulo 3, the only squares are 0 and 1, and 2 is not a square. So that you could take back and do the first question again. So looking at this question 5, if you work modulo 7, well, suppose for contradiction that x, y, z are in z with x squared plus 7y cubed z equals 5, then working modulo 7, if 2 numbers are equal, then they must be congruent modulo 7. But 7y cubed z is congruent to 0 mod 7 as well. You can forget it. So modulo 7 7y cubed z is congruent to 0 mod 7. So we would have, let's call that star, from star, x squared congruent to 5 mod 7. But that's impossible. We know that there's no integers which are congruent to 5 mod 7 from question 4. That's impossible. This contradicts question 4. X squared is congruent to 0, 1, 2, or 4 mod 7, and none of those are congruent to 5. So it's a rather quick way, in some relatively easy settings, to show that some equations can't be solved with integers. Sometimes there's some particular modulus, in this case 7, which makes it come out really quickly. Okay, I'll stop the recording there.